Can you see this?
No, I can't right now. Let's see.
Oh no. Wait, am I not? I just might not be sharing my screen. Oh my goodness. Yeah.
Oh,
Um,
there we go. Okay,
how
you're
about
you're
this?
good now. You're
Okay.
good now.
Wow, you let me go on for a while. Okay. So, all right, so let's talk about what makes a storm hazardous, right? A strong mesocyclone, right? The stronger your meso, the stronger your tornadoes, right? Your lesson of the day. But there's a lot of other things that can actually make a supercell pretty hazardous. And one of them is storm size, right? Like this gargantuan supercell off the bottom right here. And right, bigger storms can actually produce worse hazards, right? Stronger winds, bigger hail, and even larger tornadoes, the kind that are actually genuinely dangerous to spot around. So check out these two images here, right? And you could probably tell me which of these two supercells is more hazardous just based on its size, right? You can see this storm has quite a larger circulation here, a bigger hail core compared to this little dinky storm. And this is the one that is truly dangerous. So, right, like these bigger storms can produce kind of more impactful hazards and just be more dangerous to spot around. So right, our case on the left here, these really can give you violent tornadoes, giant hail, high winds, the whole shebang. Whereas these little guys that often y'all deal with up in the Midwest, sometimes they barely even have any lightning. So these are actually my favorite to spot because they're a lot less hazardous as a storm chaser. And they can look beautiful sometimes, right? Like the plane style mini supercell, a lot of people refer to as like the LP, the low precip storm. So we really got to look out for the environments that produce these chasers because they're really fun to be around. So how do we predict storm size then? Because that's kind of a newer topic in research that I think is going to actually help us a lot while we're out in the field. First off, the kind of no brainer one is the equilibrium level. How high is the top of our storm cloud, right? In this case, we're rocking almost 14 kilometers here in the troposphere. Whereas this case right here, we're only 7 kilometers deep, right? So this is kind of our mini supercell profile. Shallower storms are generally a lot less hazardous than these really big storms. And these deeper storms, what we've actually been finding in research, can especially be hazardous in terms of hail. So the deeper your cape profile here and the taller your equilibrium level, the more risk that you have that this storm could really produce some larger hail. That's a lot of it is just because the storm can loft that hailstone within it for a much longer period of time. But there's another thing that can help us predict storm size, and that's from the hodograph. And that's actually the storm relative inflow. So if you're familiar with hodographs, all we're going to do is we're going to find our storm motion here. And then we're going to draw kind of an arrow to the lower levels of the profile, right? What the storm is feeling near the ground. And so the length of the storm relative inflow is actually going to help us figure out how big your storm can actually become. Whereas when we talk about equilibrium level height, that was a lot of how tall your storm can get. With the hodograph, it's going to tell us how wide our storm can get. And how this works is that stronger inflow into the storm, it's actually pretty intuitive. It generally means that there's more mass, more moisture being fluxed into the storm at any given time. So the stronger your inflow, the stronger your mass flux, you can just get bigger updrafts. And so I'll show this comparison here. Whereas this little itty bitty mini supercell was probably formed by a hodograph that looks something like this. This really large supercell here was formed by a hodograph that looked like this, right? So their size, their width is proportional to how strong that storm relative inflow is and how long that arrow is that you drew from that right mover to that low levels of the hodograph, right? So, I can give you some example cases, right? These are what I call kind of the mega maker hodographs. And I'm going to scroll through these and you can see the image of the supercell on the bottom here and how it takes up the entire frame right now. And then you can see how strong your storm relative inflow is. So in this case, we're rocking almost 45 knots here at 0.5 kilometers. So that's really strong storm relative inflow. Going to give us a really big supercell like this. So I'll scroll through a lot of these really kind of elite tier massive supercell cases. And the point is, you don't really get this kind of environment in the Midwest very often. But when you do, it's definitely something to pay attention to. I know this might happen just a little bit more in kind of the early spring and then maybe again in late summer months. But otherwise, the Midwest tends to be a lot more tame than this. Look at these cape profiles here too. This one extends all the way up to almost 15 kilometers. So this is a Goliath of a supercell here. And these are the kind you really don't want to mess around with once you're under them. So we'll shift gears then and look at what I call the mini maker sounding. And look at some profiles of supercells. This one was actually in Indiana, and what these might look like in comparison. You can see compared to these storms, these supercells are puny. We got really weak storm relative inflow here. We have really skinny cape, and this is how you get your beautiful LPs, or in the Midwest, it might be a little bit more grungy mini supercells. And so I'll scroll through a few of these. You can see the size of these rotating supercells. This was tornadic. And then the profiles that created these very small photographs dominated by a low-level shear, which is how you get rotating storms. This one was fascinating. This actually produced a tornado in Oklahoma. Really itty-bitty storm. Had a 6-kilometer depth and a really nice photograph in those low levels. All these actually produced tornadoes that I'm aware of, except for this one. So now that we've gone through storm size, right, these are kind of our environmental predictors. What else can make a storm hazardous? Well, we could chalk a lot of this up to chaos, right? I mean, look at that radar loop. Look at how many things are going on. That storm has an insane morphology. And look at off to the right, right? We have storms like this one that have like a wall cloud up front, and then maybe some like dangly bits in the middle, and then another wall cloud in the back, right? Some of these storms can be really hard to decipher. And so we want to figure out, okay, what are actually the sources of this chaos? Can we break this down a little bit to make these storms kind of a little bit easier to understand? Well, there's a few of them. Storm cycling, right? You can see off to the right, the storms just rapidly spinning, producing new mesocyclones, new hook echoes. Each new cycle is another hazard for spotters. Deviant tornadoes is another one. Tornadoes that suddenly shift direction and motions within the storm that take storm chasers off guard. And then storm interactions, right? Storms that play with other storms and merging and Fujiwaras and all those kinds of things. We're actually going to break some of that down. So when it comes to storm cycling, we know that, you know, if you're under a prolifically cyclic supercell, it could be really easy to kind of fall behind or kind of forget that another mesocyclone is forming, and you have all this chaos in the moment. So this can actually make some pretty hazardous spotting. So we need to know how to predict this. Some storms are a lot more hazardous than others. Here's a case on the left. You see 4 different mesocyclones ongoing at once, at least, or maybe I just threw these here because I didn't know. But this case on the right is a lot easier to decipher. Right, we just have a singular mesocyclone. I mean, we can actually get some insight into how these storms are going to behave based on the environment. And I'm actually working with Hunter Fowkes from Iowa State to try to figure out how this works and how we could actually predict this. So can we? And the answer is we actually can. There is usually a difference in the structure of these storms. For folks used to watching radar obsessively during like the early spring months on the southeast, you've kind of grown to know and love this shape of a supercell. And this is really what gives you your long tracking storms. I've heard a lot of people call this like the Dixie long necker, like it's got this really long kind of neck to it. Whereas our cyclic storms tend to look a lot more classic plains-like. You might have this more kind of horizontal appearance with these hooks that kind of kick out beneath the storm. So there's a whole geometry to these storms that's contributing to how they actually can maintain tornadoes. And you can actually see that the photographs between these two kinds of storms over a lot of cases tend to be pretty different. Usually your long tracker photographs look something like this. You have really strong little shear, and you also have quite a lot of shear loft, and you might have really strong outflow to help kind of ventilate your precip away from the storm. Whereas our more cyclic type storms tend to have this more classic plains kind of half circle look, where a lot of our shear is kind of in the mid levels here. We have weaker shear in the low levels, and we also have kind of weak outflow in the upper levels. So really, you know, just jot this down or keep this in your memory. I'm sure I have some other resources online. But this is kind of what you're going to be looking at, I guess, stereotypically in terms of how your storms could behave. And I will say that these kind of long tracker photographs are a lot more common in the early season, especially up there. Whereas in the midsummer months, you might get something that looks a little bit more like this. So here's just some examples of how these photographs look in real life. I like to call these the forever mesophotographs because sometimes these storms really can maintain a mesocyclone for a very, very long time. And I'll scroll through some of these and the radar appearance on the bottom. You can see pretty much all of them have this really kind of long, necky appearance here. Lots of low-level shear here. And I'll just keep going. This was the Bassfield storm. This was another, I believe it was a high-risk storm, maybe a moderate. And then this was the infamous Mayfield quad state tornado, so if you will. So all have very similar photographs here. If you see something like this in the wild, it's usually time to start sounding the alarm bells that tornadoes could be particularly long tracked, because these have a history of producing these kind of tornadoes. Whereas this is kind of what I like to call the serial cycler photograph. It's a lot different of a shape. Your low level shear kind of juts out a little bit and shifts directions really quickly. I'll give a few of these, and you can see the supercell structures are a lot different than our long tracker cases. And I'll just keep scrolling through these. A lot of these supercells, this is the Dodge City, produced multiple tornadoes in a really short period of time. This one had at least 2 ongoing. This was the Cole, Oklahoma day earlier this year. And this was this supercell, what was it? The Akron Tornado Fest produced up to 30 little tornadoes in a really short period. So definitely something to look out for. If you see this kind of photograph while chasing, you're generally in good company with some pretty memorable events. So definitely remember that. But now let's shift gears to deviant tornadoes. This is another source of chaos that I feel really passionate about because this was actually my very first research project that I think got me on the map a little bit. And deviant tornadoes are really a life-threatening hazard to chasers, right? Because this was the El Reno case, right? I don't have to explain what happened there, but this can happen to anyone. Next year, like there will be deviant tornadoes that get close to chasers, and we have to try to figure out how to avoid that situation. So we've noticed for a while that these tornadoes can take deviant left turns. Here's the Greensburg tornado family, all over the course of one night from one supercell. It's almost like all of these tornadoes are kind of magnetically pulled up to the north. You can see even in the beginning, all these tornadoes are moving due north. Then they take these kind of curves or sudden turns up to the north, like they're going toward this magnet. And this process starts at occlusion. So as soon as you see this deep kind of occluded mesocyclone, this horseshoe shape, this is when you can start to get this going on. And what we've noticed is that these tornadoes can actually detach from the parent storm here. This is just a beautiful image here. I don't think I've seen anything that shows this better. But these tornadoes literally rip apart from the parent storm. You can see the sculpted mesocyclone here. Then you can see that gap here, that rift between the mesocyclone and the occluding tornado. And so once they do that, that tornado just stops moving with that parent supercell, and it's kind of left to just do whatever it wants to. And so when it is left behind the parent storm, what does move it is the wind and the low levels of the atmosphere. So what we're finding is that these sudden left turns are really just that low level jet in action, just pushing that tornado away from the supercell. Like we're done, get it away, on to the next one, which is really fascinating. And so this is kind of what this might look like as a close up. You can see that this tornado here is tugged to the right by the parent storm. You can see all of its cloud mass and its wall cloud kind of drifting off to the right. But you can see the tornado itself and the low levels being tugged off to the left by that low level wind. So we kind of have this tug of war balancing act. You can see the tornado in the center doesn't even move. it just keeps getting stretched and tilted, which is really cool to watch. But this just all means that you could predict it, right? You can find your parent storm motion here. So if you know that we're going to have a day with a really humped photograph, especially, these can be really conducive to deviant tornadoes. This is something that you got to be looking out for, right? Just ask yourself, could our tornadoes deviate on this day? Is this something I should be concerned about? And so you can find your right moving storm motion here. And then we could find our mean wind in the lowest, say 500 meters. That's what we found works best, right? Again, this is just these tornadoes are being swept out of the supercell by these low level winds. So we find the mean wind there. Then we just take the average of the two. The tornado is going to want to do something that's kind of influenced by the tug of war, by the supercell and the mean wind. You're going to have something in the middle of that. So what this looks like in practice, right, is your supercell kind of moves down to the south here, and then your individual tornadoes form and immediately spin off to the north. So if you were a spotter up here, right, this is bad news for you. You don't want to be up here. And obviously this is really surprising, right? A southward moving supercell, you would not expect your tornadoes to have to deviate up north. That's what happens. So let's do a case study. Well, let's do some practice. Look at this photograph right here. First of all, find storm motion. That's the easy part, right? You want that bunker's right, that right motion. So let's drop a little dot here. Let's start with that. Now, where's our low level mean wind? Right? You can find that. Where is it? It's up here somewhere, right? Take our lowest kind of shear vector and kind of take the middle of that line here. Let's take an average. Doesn't have to be exact. You don't have to do this on a calculator. And then, right, how could a tornado move, right? If it's going to be influenced by both that right moving supercell and this mean wind, where do you think a tornado is going to move? Where do you think its vector is going to be on the photograph? It's going to be somewhere in the middle. So we could plot that right here. And so, right, you could draw that vector, and then you could see that tornado has kind of a northeast component to its motion. So this is for any potential tornado that comes from the supercell, right? Not all tornadoes are going to do this, thankfully, but some do. So envision yourself, right? Now you're chasing a storm here, and you want to figure out, right, is this storm dangerous? Are you safe here? And like your first gut reaction is going to be like, yeah, I'm totally fine. Look at that. There's a tornado all the way down here, right? It's moving due east. We're totally good, right? Surely you're good here, right? Like you're good. Everything's fine, right? You can do some mental math here, right? You're 9 miles away from that tornado. You're definitely safe, right? We're good. You're so good. Let's loop this. Boom. So that's what you want to avoid in this scenario. So like if I ever had a mantra for this, it'd just be never go north, right? You remember Skip Talbot's video, right? Should we drive south? And that's a really good question because a lot of these tornadoes, especially El Reno, that was another case where these tornadoes deviated quickly north. Don't let this be you, right? Do these really simple calculations beforehand. If it's a day with a really big hump photograph, it's probably one that you want to avoid going north in the cold. This really could be you one day. I'm just trying to avoid that. So in real time, you could actually use Tim Sapini's VAD wind profiler. It's on autumnsky.us/VAD, this little link on the bottom here. I'm not sure if you could see this, if it's covering it up, so I'm going to move it. But this can actually show the deviant tornado motion vector on there. So that's really cool for like a real-time photograph viewer. And you can see if that's going to be an issue, right? So in this case, we did have a DTM that was almost due north. So in this case, this is going to be a case where I'm kind of concerned about deviating. So I'll show you some classic deviator photographs. This is the Andover, Kansas tornado, just from last year. Beautiful example of a deviant tornado. Watch that radar loop if you get the chance. It's really fascinating. But you could see that really big hump to that photograph. These are classic Great Plains low-level jet photographs. Oh, I have the loop in here. So we're just going to watch it deviate, right? That tornado's booking it due north, even as that supercell moves almost due east. So definitely not a good time to be sitting in Andover here, where you think you're safe, right? Because that tornado forms miles away off to the south and still ends up hitting you. Greensburg, another really good example. I'll just kind of scroll through these photographs. Very similar, especially to our cycler photographs that we talked about. So that's that on my spiel on deviant tornadoes. And lastly, I'll leave you with some fun about selenoraps. Because that's something I'm currently working on right now. I'm sitting on a lot of really cool stuff that should be out sometime by next spring. I'm really excited about this stuff and what it's going to do to really make chasing a lot safer, and even a little bit easier. I think it's done that for me at least. And some storms are really easy to read, right? They're just singular storms here. Nothing anywhere near them. You know how the storm is going to be hit, and this is going to be pretty easy to spot. But in a case like this, what do you do? What do you think is going to happen, right? Look at all this chaos here. There's all these different cells, mergers, collisions. What's going to happen, right? Cell interactions can make a storm misbehave and just do things that are a little bit untypical. I mean, things could be a little bit dangerous too if you're thinking about it. So what are some interactions that we can look out for, right, to keep us safe? First off, what I like to call forward flank mergers. Here's a classic example, right? This is your canonical traditional storm merger. A lot of storms go up. They all kind of crowd together and ultimately create a much bigger storm, because what we're doing is we're just piling on updrafts and mass into that storm, and it's just getting bigger and bigger and bigger. So usually these storms are kind of a breeze to spot. You just got to wait for the merging to finish, right? Wait until you get a mature updraft out of these. Usually the new storm ends up taking over and becoming mature, and then your next step is profit. But here is a type of merger that is a little bit more almost sinister. This is called I just call this one the rear flank merger. Instead of the forward flank, these come out of the rear, and these can induce some pretty dramatic and quick changes to your storm while we're chasing. And these can be really hazardous to you as a spotter. So let's slow this down a little bit and see what's actually going on. Say you're chasing this supercell near Amber, Oklahoma here, and you're just sitting here on the highways. Perfect spot. You're watching a rapidly rotating wall cloud. The storm is moving really slowly, kind of just at a clip north of you. So you're totally good. You're safe here. This supercell's just kind of, this is your classic I-44 rider. So as we continue upward, the storm even starts to stall, right? You're in a prime viewing spot. Look at that hook echo right there, right? Like you've got it made. Like you're watching the storm. It's just sitting there, not moving at all. Just a beautiful, pretty perfect scenario for a chaser. But what you're not noticing is the cell coming in behind it, right? And so this cell also has emotion. This cell never stops moving. So ultimately, right, you sit here and what's happening? You get hit, right? This happens over a course of 15 minutes. And you're just sitting here watching a beautiful show, and all of a sudden, this supercell just comes barreling toward you. So I'll kind of run this loop again. You can see how this rear cell here poses a huge hazard if you're not aware of it at the time, because the supercell ends up taking on that motion of this cell and running kind of due east right into you. So this is all to say that, like, while you're out there spotting, right, it isn't just your supercell. Don't get tunnel vision. It's your supercell and all of its friends, and usually more than one storm is a bigger danger than just one storm by itself. So I'll go through a kind of a similar case. This is what's known as a Fujiwara, two supercells with big enough mesocyclones that they're literally inducing each other's motion and even the hazards that they produce. So I like to call this kind of the old reliable of tornado chasing, right? Because after this Fujiwara, very, very often there is a high probability that a tornado actually occurs. So there's my little meme for this. Yeah. But how do you play the Fujiwara then? Well, let's say you're out on the move and you're on a supercell that could interact with another supercell and produce a tornado after. What are you supposed to do in this situation? Fortunately, a lot of these Fujiwaras actually work pretty similarly. And this is something that I've noticed out in the field. They have kind of a rhythm to them, like a step-by-step what these storms actually do. So first off, you got to remember that a lot of times you can have tunnel vision, right? You're just focused on this one supercell that you're on. Maybe you haven't looked at radar in a really long time just because your supercell's slow moving or really pretty or what have you. Always gain situational awareness. Let's zoom out. We got another supercell here, right? This is going to cause some issues. Always be situational aware. There are two supercells here. There's not just one. So our kind of first next step then is we want to get away. Okay, like in order to maximize our safety, we need to give these storms some space because as you can see now, they're starting to take on different motions. This supercell is moving up north. This one's moving due east, and it's easy to kind of see the supercell you're on start to move north and away from you, and then you're like, oh no, I got to catch up to it, right? I got to get closer. Whereas what you don't see is this next supercell barreling toward you. And again, the storm behind the supercell is usually hidden, right? Because we have a big kind of shelf cloud mesocyclone structure. It's really often that you can't see this rear cell come in, as big as this looks. So my first word of advice is really just to get away, just find a spot that's far enough away that you could wait for this interaction to play out. And my kind of hint here is that usually there isn't even a tornado while these cells are interacting. That's just something I've noticed. Don't quote me on that, but usually while this messiness is ongoing, you're really not missing much anyway. So it's this is usually a good time to reposition, give them some space, sit somewhere far away. And you know, at some point during the merge, things are going to look really messy. I've actually been caught off guard by how messy these storms look. You know, you look at this and you're like, I don't see a tornado happening anytime soon. But you really got to trust the process. And this was the very next 15 minutes later. We had an EF3 tornado ongoing. Or was it a two? It was a significant tornado going straight into Shawnee. So a really dangerous situation. And again, it's usually right after this Fujiwara completes, and at the very first kind of instance in time where we really only have one supercell here and not this pair. So this is again a pretty reliable way to get a tornado. If it's going to happen, it's often after one of these